The kinetic particle theory is a fundamental principle in understanding the behavior of gases, liquids, and solids at the microscopic level. This theory explains how the particles, atoms or molecules, in a substance are in constant motion, even in solids. The degree of particle motion and the interactions between particles determine the state of matter, gas, liquid, or solid. In gases, particles have the highest degree of motion and are widely spaced, resulting in low density and high compressibility. In liquids, particles have moderate motion and are closer together, resulting in higher density and lower compressibility. In solids, particles have the lowest degree of motion and are tightly packed, resulting in high density and low compressibility. Understanding the kinetic particle theory is crucial for explaining and predicting the properties and behaviors of different states of matter. This theory has many real-world applications, such as in the design of materials, the development of new technologies, and the understanding of natural phenomena. The kinetic particle theory is a model that explains the behavior of matter in terms of small, discrete particles in constant random motion. It forms the basis for understanding the states of matter and the relationships between them. The theory proposes that all substances are composed of tiny, constantly moving particles, such as atoms or molecules. These particles interact with each other through collisions and attractions, resulting in the macroscopic properties we observe. This microscopic perspective helps us understand the underlying mechanisms that drive the physical properties of materials. The kinetic particle theory explains how particles behave in the three states of matter: solids, liquids, and gases. In solids, particles are fixed in position and can only vibrate. In liquids, particles can slide past each other with some freedom of movement. In gases, particles move rapidly in random directions with complete freedom of movement. The slide shows colorful icons representing the different particle motions in each state of matter. Particles possess thermal energy, which causes them to move constantly and randomly in all directions. As the particles collide with each other and the container walls, they transfer kinetic energy, maintaining the random motion. While the motion of individual particles is impossible to predict, the overall behavior can be described statistically. The constant, random motion of the particles is a fundamental characteristic of thermal energy and is essential for understanding many physical phenomena. Kinetic energy is the energy of motion. It depends on the mass and velocity of the particle. Mass is the amount of matter in the particle. Heavier particles have more kinetic energy at the same velocity. Velocity is the speed of the particle. Kinetic energy increases exponentially with higher velocities. Small increases in velocity can have a large impact on the overall kinetic energy. The formula shows the relationship. Kinetic energy is directly proportional to mass and the square of velocity. This means that even small changes in velocity can dramatically change the kinetic energy of an object. Kinetic energy is the energy of motion. It depends on the mass and velocity of the particle. Mass is the amount of matter in the particle. Heavier particles have more kinetic energy at the same velocity. Velocity is the speed of the particle. Kinetic energy increases exponentially with higher velocities. Small increases in velocity can have a large impact on the overall kinetic energy. The formula shows the relationship. Kinetic energy is directly proportional to mass and the square of velocity. This means that even small changes in velocity can dramatically change the kinetic energy of an object. Particles collide with each other, exchanging momentum and energy, causing changes in their motion and direction. Particles also collide with the walls of their container, transferring momentum and creating pressure on the surfaces. In a confined space, particles continuously collide with each other and the container walls, driving the dynamic behavior of the system. These collisions are fundamental to understanding the behavior of particles in various physical systems. The pressure exerted by a gas is caused by the constant collisions of gas particles with the walls of the container. When particles collide with the walls, they transfer their momentum, resulting in a force that we measure as pressure. The pressure in a gas fluctuates as particles collide with the walls, but the average pressure remains constant. Increasing the number of particles or their speed results in more frequent collisions, which increases the overall pressure. Temperature is a measure of the average kinetic energy of the particles in a substance. Higher temperatures mean the particles have greater average kinetic energy. As temperature increases, the particles move faster and collide more often. This increased particle motion and collision results in greater overall pressure. The relationship between kinetic energy and temperature is key to understanding many physical phenomena. As temperature increases, the average kinetic energy of the particles in a substance also increases. This means the particles are moving faster and with greater force. This increased kinetic energy can cause substances to expand and even undergo phase changes like melting and boiling. For example, as water is heated, the increased kinetic energy of the water molecules causes the substance to expand and eventually transition from a liquid to a gas. Understanding this fundamental connection between kinetic energy and temperature is crucial for explaining many observable changes in the physical world around us. Solids are characterized by tightly packed particles, typically atoms or molecules, that are confined to fixed positions. These particles exhibit constant vibrations around their fixed points, with only limited movement possible. Particles in a solid have low kinetic energy compared to other states of matter, as they are restricted from free movement. Their vibrations are limited to small, rapid oscillations around their equilibrium positions. The image on the slide shows a molecular model of the vibrating crystal structure in a solid. The particles in a solid are tightly packed and held in fixed positions by strong intermolecular forces. When a solid is heated, the particles gain kinetic energy and vibrate with increasing intensity around their fixed positions. Despite the vibrations, the particles in a solid maintain a highly organized, crystalline structure with a defined shape and volume. This vibration of particles is a key characteristic of solids and helps explain their rigid, stable nature. The vibrations occur because the thermal energy provided by heating causes the particles to move back and forth around their fixed points in the crystal lattice. The key point here is that particles in a solid have very low kinetic energy compared to other states of matter. This is due to the restricted vibration of particles within their fixed positions in the solid structure. Solid particles are limited to just 3 degrees of freedom. They can only vibrate in the x, y, and z axes. As a result, most of the thermal energy in a solid is actually in the form of potential energy from the atomic bonds, not kinetic energy of the particles. This low kinetic energy of particles in a solid is an important characteristic that distinguishes solids from other states of matter. Liquids are made up of particles that are able to slide and flow past one another. The particles have enough kinetic energy to overcome the attractive forces between them. This allows the liquid to conform to the shape of its container. The random, constant motion of the particles enables this sliding and flowing behavior. This sliding motion and lack of fixed particle positions is a defining characteristic of the liquid state of matter. The image on the slide shows this flowing, sliding motion of particles in a liquid. Liquids are characterized by the ability of their particles to slide past each other freely. This is due to the relatively weaker intermolecular forces between liquid particles compared to solids. Liquid particles exhibit constant random motion, colliding and changing direction frequently as they flow. This random motion is driven by the kinetic energy of the particles, which is high enough to overcome the attractive forces between them. The combination of sliding motion and random movement allows liquids to flow and take the shape of their container. Liquids have higher kinetic energy compared to solids due to the ability of their particles to slide past each other freely. This increased movement and kinetic energy allows liquids to take the shape of their container and flow more easily than solids. Solid particles only vibrate in fixed positions, while liquid particles can slide past each other. The sliding motion and higher kinetic energy of liquid particles is what enables liquids to be more fluid and adaptable than solids. Gas particles have no fixed positions and move freely in random directions. They constantly collide with each other and the container walls, resulting in rapid, erratic motion. The kinetic energy of gas particles is directly related to their temperature. Higher temperatures lead to greater average kinetic energy and more vigorous particle motion. The image shows an abstract representation of this random, chaotic motion of gas particles in a container. gases have the highest kinetic energy compared to solids and liquids. This is because gas particles are free to move in all directions, colliding frequently with each other and the container walls. The constant, rapid movement and high frequency of collisions in gases result in very high average kinetic energies for the particles. Some key facts. Gases experience over 1 billion collisions per second. The average kinetic energy of gas particles is 10.5 joules. Gas particles can reach top speeds of 30,000 miles per hour. There are around 10 to the power of 23 gas particles per liter. This high kinetic energy is a key factor in understanding the behavior and properties of gases. Gases are made up of particles that move freely in all directions, constantly colliding and bouncing off each other and the container walls. This random, chaotic motion is what gives gases their dispersed, low-density nature. Unlike solids and liquids, gas particles have no fixed arrangement and can move independently throughout the available volume. This free movement and lack of structure is a key characteristic of the gaseous state. The changes in particle motion and energy during phase transitions like melting and boiling are illustrated in this detailed cutaway diagram. The kinetic particle theory explains how temperature and pressure affect the motion and energy of particles, leading to phase changes like melting and boiling. As particles gain kinetic energy, they can overcome the attractive forces holding them together, allowing them to transition between liquid and gas phases through evaporation and condensation. During melting and boiling, the kinetic energy of particles increases, allowing them to overcome the intermolecular forces that hold the substance in a solid or liquid state. The melting point is the temperature at which a solid substance changes state and becomes a liquid. This happens when the kinetic energy of the particles overcomes the intermolecular forces holding the solid in place. The boiling point is the temperature at which a liquid substance transitions to a gas. At the boiling point, the kinetic energy of the particles overcomes the intermolecular forces, causing the liquid to vaporize and form bubbles. Understanding melting and boiling points is important for many applications, from cooking to chemical processing. Knowing these key phase transition temperatures helps us predict and control the behavior of materials. The images on this slide provide a visual representation of the melting and boiling processes, which can help the audience better understand these fundamental concepts. Evaporation occurs when the kinetic energy of particles in a liquid is high enough for some to escape the surface and enter the gas phase. Condensation happens as gas particles lose kinetic energy, slow down, and cluster together, transitioning back to the liquid state. Evaporation and condensation are key phase changes that occur when substances change between liquid and gas states, driven by changes in particle kinetic energy. The image depicts water droplets forming on a cold surface, with steam rising in the background, creating a serene, misty atmosphere that illustrates these concepts. The kinetic theory of gases explains the fundamental relationships between the pressure, volume, and temperature of gases. Boyle's law states that the pressure of a gas is inversely proportional to its volume. The kinetic theory demonstrates how this occurs due to the movement and collisions of gas particles. Charles's law describes the direct relationship between a gas's volume and its absolute temperature. The kinetic theory accounts for this by showing how increased temperature leads to greater kinetic energy and movement of gas particles. Avogadro's law states that equal volumes of different gases at the same temperature and pressure contain the same number of particles. The kinetic theory explains this by modeling how gas particles behave similarly regardless of the specific gas type. These gas laws and their kinetic theory explanations are foundational to understanding the behavior and properties of gases. Boyle's law states that pressure and volume of a gas are inversely proportional. As pressure increases, volume decreases, and vice versa. The diagram visually demonstrates this relationship. An increase in pressure leads to a decrease in volume. A decrease in pressure leads to an increase in volume. This inverse proportionality between pressure and volume is a fundamental principle in gas behavior. Charles's law describes the relationship between the volume and temperature of a gas. It states that the volume of a gas is directly proportional to its absolute temperature when pressure and amount of gas are held constant. The chart on the slide shows the change in volume as the temperature increases from 273 K to 573 K. We can see that as the temperature goes up, the volume also increases in a linear fashion. This demonstrates the key principle of Charles's law, that volume and temperature are directly related for a fixed amount of gas. Understanding this relationship is important for applications like gas storage, engine design, and other areas where gas behavior is a factor. Avogadro's law states that the volume of a gas is directly proportional to the number of moles of gas at constant temperature and pressure. The equation for Avogadro's law is V equals N asterisk K, where V is the volume, N is the number of moles, and K is a constant. This fundamental gas law helps explain the behavior of gases and is crucial for many chemical and physical calculations. The diagram on the slide illustrates the relationship between the volume of a gas and the number of gas molecules or moles. Understanding Avogadro's law is essential for predicting the behavior of gases in chemical reactions and processes. The ideal gas law describes the relationship between the pressure, volume, temperature, and amount of gas particles in a system. This law can be derived from the kinetic particle theory, which models gases as a collection of constantly moving particles. The variables in the ideal gas law, pressure, P, volume, V, temperature, T, and moles of gas, N, are all related by the kinetic energy of the gas particles. While the ideal gas law is a simplified model, it provides a good approximation for the behavior of real gases under standard conditions. The kinetic particle theory is a fundamental concept that helps us understand the properties and behavior of materials at the molecular level. This theory is crucial for advancements in materials science and engineering, as it allows us to study and manipulate the behavior of materials to create new and improved products. In the field of meteorology and atmospheric science, the kinetic particle theory provides insights into the movement and interactions of gas particles, which is essential for understanding and predicting weather, climate, and other atmospheric phenomena. Many industrial processes, such as refrigeration, combustion, and fluid dynamics, rely on the principles of the kinetic particle theory to optimize efficiency and performance. By understanding how particles behave and interact at the molecular level, we can design and improve industrial processes to be more effective and sustainable. The field of materials science and engineering is all about understanding how the atomic and molecular structure of materials impacts their physical properties. This knowledge enables material scientists to design advanced materials for a wide range of engineering applications. For example, the kinetic particle theory helps us understand how particles behave in different states of matter. This informs better manufacturing processes, allowing us to control temperature, pressure, and predict phase changes during production. Kinetic particle theory principles are also crucial for ensuring the structural integrity and safety of engineered products, from buildings and vehicles to consumer goods. Furthermore, these insights enable the development of innovative technologies, such as high-performance materials, energy-efficient systems, and nanotechnology applications. In summary, materials science and engineering is a critical field that underpins many of the technological advancements we see in the modern world. The dramatic aerial view of the storm system over the city sets the stage for the importance of meteorology and atmospheric science. Satellites provide a bird's-eye view of weather patterns, allowing meteorologists to track storms, cloud formations, and other atmospheric phenomena in real time. Ground-based weather stations collect crucial data on temperature, humidity, wind speed, and other variables, providing inputs for forecasting and climate modeling. Sophisticated computer models simulate the complex interactions of atmospheric gases, pressure, and energy to generate weather forecasts and climate projections. These three key technologies, satellite monitoring, weather stations, and predictive models, form the foundation of modern meteorology and atmospheric science. The key concepts of the kinetic particle theory that we've covered are particle motion, particle interactions, changes of state, and the gas laws. Particles in solids, liquids, and gases exhibit constant random motion, with their kinetic energy, depending on temperature. Collisions between particles and gases create pressure, while particles in liquids and solids have more constrained motion. Differences in particle motion and kinetic energy explain the processes of melting, boiling, evaporation, and condensation. The kinetic particle theory underpins fundamental gas laws like Boyle's, Charles's, and the ideal gas law. These core concepts provide a unified explanation for the behavior of matter in its various states.